Welcome! Today we're going to have a look at double and triple integrals. So we're going to consider double and triple integrals and their meaning and how to calculate them. Example 5.1. Let f of x and y be equal to x over xy squared over x squared plus 1. And then consider this rectangular region where x is between 0 and 1 and y is between -3 and 3. Okay, so that is this region here. X is between 0 and 1, and y is between -3 and 3. So that puts our axis, x-axis, through here, and the y-axis here. When you're looking down from above, okay, of course, the z-axis comes up. And so here we have a three-dimensional image of it. And better yet, you can see it on the left of my screen. So let's talk about the top view. We've got x going from 0 to 1, y going from -3 up to 3. So this is this region, the yellow region there. Okay, the function, well, that gives you a surface. Z is equal to this, f of xy. And so you see the height of that changes as you move around. So what we're doing in this example here is we're going to calculate the volume of this yellow piece. Right? So you can see that the base of it is rectangular. The height of it varies according to this green surface. Okay, and so how you do that is with a double integral. So if this inside here, from the top view, is the rectangular region R, we're calculating the volume of that solid-looking yellow piece inside, as a double integral over the region R of f of xy dA. Now dA is an infinitesimal piece of area. Since f of xy is continuous in the region, we can use Fubini's theorem below to calculate the volume by integrating twice two definite integrals treated partially, as in something like this, but we don't use this notation. We use an ordinary d in our notation. But hey, you might argue that this would be better notation. Okay, so what Fubini's theorem says is that you can calculate such an integral in two ways because this is a rectangular region, which makes that easy to swap around. So Fubini's theorem is the statement: if f is continuous on the rectangular region, x goes from a to b, y goes from c to d, then the double integral, and you may as well change that d into an r if you like, so it matches what we have up there, but it doesn't really matter. So the double integral of this function over the region d can be expressed as the integral of f of xy integrated with respect to y from c to d, and then integrated with respect to x from a to b. Okay, now the theorem says that you can swap this around quite easily because it's a rectangular region. So you could integrate that the other way, integrating first with respect to x and then with respect to y. And you just swap things around, right? So this goes with this goes with this. So you're swapping the order of the integration as well as these, right? Remember, this just says with respect to and with respect to. So when you swap, you also swap these. They both swap at the same time. Okay, next page. Calculate the volume shown in figure 29. So that's this one here. But we can look at what I have on the left of the screen. So calculate this in two ways using Fubini's theorem. So let's just remind ourselves and sketch a little rectangular region. So probably do that in the corner. Here we've got an x-axis and a y-axis. Okay, our rectangular region, x goes from 0 to 1, and then y goes from, say, -3 to 3. So our region R is inside here. Right, so this is in the xy plane, and remember we have a surface above that and we're calculating the volume under that surface. Okay, so the volume is given by double integral over the region R of f of x and y. Now we can do this with respect to either one of the letters first. So we first write this dA, and then we'll change this so that we write it in terms of one of the letters first. Okay, so if we put dy first, then dx is second, we're integrating f of x, y. Now as y goes from -3 to 3, right? Y goes from -3 to 3. X goes from 0 to 1. All right, now the function is xy squared over x squared plus 1. But we'll write this x over x squared plus 1 times y squared. Now remember, integrating this with respect to y means that we're treating x as a constant in that integration. So at this point we'll integrate this with respect to y, so the integral of y squared is y cubed over 3. So we can write 1/3 x over x squared plus 1 y cubed, and then that's integrated from y equals -3 to y equals 3, and then we have to integrate the result with respect to x. Now I'll come up here in this blank space to continue. So let's have a look. 3 cubed is 27, but 27 over 3 is 9. So coming up here, this is the integral from 0 to 1 of 9x over x squared plus 1. And then when we cube -3, we get -27. So -27 over 3 is -9. So we are subtracting this times -9. And so that becomes plus, when we subtract, plus 9x over x squared plus 1. Okay, now we have a simple function of x, relatively simple. So we're going to integrate from 0 to 1, pulling out, so 9 plus 9 is 18, but let's pull that out the front, and that's just factorization. So 18 times x over x squared plus 1 dx. Okay, now at this point, we've got a simple integral, but to finish it off, we want to make a substitution. So let's go ahead and make that substitution. U equals x squared plus 1. And the reason why this works is because the derivative of that denominator is some multiple of the numerator. So we're going to get something times the natural logarithm of x squared plus 1. But let's do this properly. So u is equal to x squared plus 1. Now we want to differentiate. Take du on dx, and so we get 2x for that. But what that tells us is how to make a replacement in an integral by substitution. So what this says then is to replace dx with du over 2x. Okay, and now how do we determine that that's what we do? Well, what I'm doing in my head here is I'm algebraically rearranging this as if this is a fraction. However, it is not a fraction. that is only an aid to memory of the rule of integration by substitution. Right, but it's a good way to think about this, right? Don't say that they're fractions because they're not, but in aid to memory of the rule, you can rearrange this and then say that you're making this substitution. So what we have then is that the volume is 18 times the integral from 0 to 1 with respect to x of x over u, right? But as soon as we make this replacement here, we've got to change the bounds of integration also. So we have x over u, and then replacing dx with du on 2x, du on 2x. So now it's an integral with respect to u, and so we have to change the bounds here to those corresponding bounds in terms of u. So to work out what those are, we have u as a function of x when x is 0, is 0 squared plus 1, and that's just 1. Now u as a function of 1 is 1 squared plus 1, which is 2. So our new bounds are 1 to 2. And you can notice that the x's cancel, so this means that that substitution up here is the appropriate one. So we can cancel the x's, and so we've got 18 integral from 1 to 2 of u to the minus 1 du. All right, the integral of 1 on u, or u to the minus 1, is the natural logarithm of u. So we have 18 ln, or log as I would write, because the natural logarithm is so natural, you may as well just write log. So log of u, and now that's u goes from 1 to 2. Okay, so subbing those values in, we have log of 2 subtract log of 1. But e to the power of 0 is 1, so log of 1 is 0. So this is just 18 natural logarithm of 2. Okay, so next, applying Fubini's theorem, we're going to swap this around and hopefully get the same number. All right, so according to, now I'll keep this page here for a little bit. So we're going to take this integral the other direction. And so we've got v equals the double integral over r, f of x and y, dA, but taking this the other way, as in integrating with respect to x first, we have x over x squared plus 1 multiplied by y, and then we're going to integrate with respect to x first and then with respect to y. All right, so now this integral, so we're treating y as a constant when we do this, so we've got to integrate this with respect to x, but we've essentially just done this, right? So knowing how this turns out, but you can set it out again, as in set out let u equal x squared plus 1 and complete that again. So what we have is this is going to be 1/2 natural log of x squared plus 1. And since I've left this in terms of x and not changed this to a letter u, this is x equals 0 to x equals 1. All right, good. So now we sub that x is 1 in. We've got log 2 and then subtract log of 1. So this is integral minus 3 to 3 of 1/2 natural log. 1 plus 1 is 2. And then we would be subtracting 0. All right, good. So now we want to, oh, we've forgotten the y, haven't we? So the y goes in there, and so the y is still there. Okay, so now integrating this with respect to y, We add 1 to the exponent of y, divide by the new exponent. So we have 1 over, see, new exponent is 2, so dividing that by another 2, so we've got a quarter natural log of 2 y squared minus 3 to 3. Okay, 3 squared is 9, minus 3 squared is also 9, so we've got a quarter log 2 times 9, so 9 over 4. And then, oh, hang on. That was always a y squared, wasn't it? Yeah, if I look at this function, that was always a y squared. So I'm not just missing a single y. There were 2 y's in there. So this is actually, that integral of y squared is y cubed, and it's not over 4, it's over 6. Okay, so 9 over 6, and now the cube of, oh, but hang on. 3 cubed is 27. 27 divided by 3 is 9, so this should be 9 over 2. Okay, and then we have minus in brackets. Minus 9 over 2 log of 2. So this gives us, since there are 2 minus signs here, we've got plus 9 over 2 log of 2. So that's gives us 9 natural log of 2. Okay, in agreement with what we got on the previous page. Theorem 12. If f of xy is continuous on the rectangle, so we've got a rectangle, and we have a function that is a product of a function of x and a function of y, well, then we can just break this up into 2 integrals of one letter. So to see this, Fubini's theorem shows us that we can put x first, right? And since this is taken as an integral partially, well, then we can pull out the other letter in front because that's getting treated as a constant. Pull it out in front, so it's there, and then we just have this. However, so this is a function of x that we're integrating, and we're putting numbers in there, so that will be treated as a constant when we perform this integral, so we can pull that out the front of this integral, and we just have this integral times this integral, confirming what we have up here. Okay, example 5.3. Let f of x and y be x squared sine y, and let a rectangular region be x going from 0 to 1, and y going from 0 to pi on 2 radians. Okay, so here is our region. And then our surface above that we're calculating a volume of is the surface x squared sine y. Now I don't know if I have that plotted below just like this. Not quite. I have what's underneath that on the page here. Okay, but this is a rectangular region. Now, can I just copy this code and change things? Probably so. So we may as well go ahead and do that. So our function here is x squared times sine of y y goes from 0 to pi on 2, but I'll take it from from minus 1 to 2 in the plot. And then this little block I would want to change this, and I would want to change my little block as x goes from 0 to pi on 2, and then make this match. Okay, we'll have a look and see if this works out. All right, so something like this. Okay, so looking from above, you see that that yellow gives us our rectangular region. And we're calculating the volume of this surface between that region. It looks a little wedge-shaped. So it's this little volume under there. Okay, great. So let's calculate. So we've got the volume equal to integral over the region R of x squared sine of y. And then let's do this with respect to x first, and then with respect to y. It's a rectangular region, so it doesn't really matter which one you do first. So this is a function of x and multiplied by a function of y. So we can break this up into two integrals. So we've got x going from 0 to 1, x squared dx, and then integral from 0 to pi on 2, sine of y dy. Okay, great. So this is a third x cubed 0 to 1 multiplied by minus cos of y from 0 to pi on 2. Okay, so we've integrated these. Now we sub in and take a difference. So that's 1/3 1 cubed minus 0 multiplied by minus 0 minus 1, because cos of 0 is 1. Okay, so this is plus 1, so we end up with plus 1/3 as our volume of this little yellow piece under that surface. All right, so now let's move on to volume integrals over non-rectangular regions. And let's scroll down to the diagram here as well. Okay, so looking at this region, we have a curve y equals x squared. And then we have a line. I extend this back. This is the line y equals minus x. Okay, so imagine calculating a volume of a surface where this is the region. It's not rectangular anymore. So what I want to point out to you is how to take this region. So it's clear that x goes from 0 to 2, right? So x is between 0 and 2. Now what about y? So if I just take an arbitrary point inside here, so x comma y, and I draw a vertical dashed line, what would this point be? If this is the point xy here, well then this would have the same x value. But since y equals x squared there, the y value is x squared. And down here, what would this point be? Well, I have the same x value, but the y value is now minus x. So x comma minus x. Okay, and so this y is less than x squared, and it's greater than minus x. So we have y is greater or equal to, talking about this entire region, y is greater or equal to minus x, but it's less than or equal to x squared. And so the way that we would calculate an integral with this sort of setup of the region R, or D if you like. So when we have R equals the set of all x comma y such that x is between 0 and 2 and y is between minus x and x squared, well then we would set that integral up where we have the constant represented on the outside. So the constant values. You see, constant values 0 and 2. Put that on the outside. And then on the inside, put the values that depend on y, right? So minus x to x squared. In here we have f of x and y. And then that's dy dx. So the x goes with the x being between 0 and 2, and the y goes with the y being between minus x and x squared. Now you can swap this around, but you have to think about it differently. Okay, if you swap the order of integration here, then it would be x going between a function and a function, and y between a constant and a constant. Okay, now if we look at this little region here, and again think about integrating some surface where this is the region of integration, no longer rectangular. Okay, so here in this one we see that x is between a function and a function, and y is between minus 1, and up here we've got 4. Okay, so this time y is between two constants and x is bound between two functions. And so let's suppose that that's g of y and h of y. And so it looks like something like h of y might be x equals y squared or similar, right? And g of y is some linear function of y. Okay, so in this case you would write your integral the other way around, putting the constants on the outside. So you would put v equals integral from minus 1 to 4. So you'd have your f of xy here, and then you put dx dy. Okay, this is g of y, and up here you'd have h of y. This is x equals h of y, and this over here is the line x equals g of y. Okay, now this one's clearly linear, this one's quadratic. X is a quadratic function of y. Okay, so let's go ahead now and consider the details of this. So we've got our drawing, and that should tell us basically what's in the next paragraph, but let's read this while we look at that sketch and notes on the sketch. On the left of figure 30, we have a region in which x is between two constants and y is between two functions of x. So exactly what we've written there. On the right of figure 30, we have a region in which y is between two constants and x is between two functions of y. Just like we have there. X is between two functions of y. So the goal of this section is to be able to calculate the volume under the surface. So if we have a surface z is equal to f of xy and bounded by such a region. So examples like this. These regions are examples of non-rectangular regions and require more care when we need to swap the order of integration. And why would we want to swap the order of integration there if we have one expression for it? Well, it turns out that integrals are easier one way, often than they are the other way. So, for example, this is possibly not the best example to talk about the difficulty difference, but so we'll see some coming up. All right. So if the region over which we integrate f of x, y is of the form x between two constants and y between two functions of x, so for example, let's see, an example of this would be, well, here y is between two functions of x, right? So for example, this one, so let's say left of figure 30, and so when we do that, we put the constant values on the outside, and the letter that is between the two functions, we put that on the inside. Okay, so e.g. right, in this case that we had r equal to the set of all points x, y, such that x was between 0 and 2 and y was between minus x and x squared. Okay, so the way we do this, we put the constant on the outside, constant values on the outside, and the corresponding letter, so x is between 0 and 2, two constants, that goes on the outside, right? And on the inside, or the left, y is between two functions of x, so that goes on the inside. In other words, that gets integrated first. Okay, now on the other way, so on the right hand side, so right of figure 30, we do this the other way around because now x is between two functions of y. And so for example, so e.g. on the right of figure 30, we had double integral minus 1 to 4, so constant on the outside, and that was y going between minus 1 and 4, so that's dy first and then dx. Oh, hang on, no. dx first and then dy. Yes, so like this, and so that was g of y and then h of x. All right, so yeah, that pertains to this picture up here. Okay, let's move on to the next page where we're going to do an example, and it's a fairly simple example. So I wonder whether I have a picture of this down here. Let's have a look. Yes. So this is maybe a clearer picture of that triangular region. And then down below that, we've got this region here. So let's have a look around at it. So we've got this triangular region. X goes from 1 to 4, and y goes from 1 to this line, y equals minus x over 3 plus 7 over 3. Okay, but we can represent that region in two ways. And so we'll calculate this volume of this yellow piece under that surface. We'll calculate that in two ways using the previous things we learned. Okay, so first let's draw on this picture. So we've got x going from 1 up to x equals 4, right? So these are two constants. Remember, in the integral, that goes on the outside, the two constants. Okay, now what about this? So what is y between? Y is between 1, and it's under this line. So this is the line, y equals, let's see, 1/3 of 7 minus x, isn't it? If we look at that, reversing the sign of these two things, or the position of those in the expression. So here, then y is under that line, so y is less than or equal to this right here. Okay, and remember, we would write this 1 to 4 on the outside, and that's x going from 1 to 4, so we put the dx first. Or no, on the outside, we put the dx on the outside, right? Outside, and then the dy on the inside. So we're integrating x times y, and then the y goes from 1 to 7 minus x all over 3. Okay, and now in this way of representing it, the y goes from 1 to 2. So we have 2 up here. This is y equals 1. Okay, so y going between two constants, 1 and 2, but then x is between 1 and, now rearranging this incidentally, if we just take y equals 7/3 minus x over 3 and solve this for x, what we're doing here is we're multiplying both sides by 3. Okay, then we take the x over and the 3y over, and we have x is equal to 7 minus 3y. So here, in terms of x, we have x between 1 and x is less than 7 minus 3y. In that shaded region. Okay, so we write this, we write the integral, the volume under that surface within that triangular region. In the other way of writing it, we write that with the constants on the outside. So y goes from 1 to 2, and then that is with respect to y. And then on the inside, x goes from 1 to 7 minus 3y. That's of xy with respect to x. It's the x that is between the 1 and the 7 minus 3y. Okay, so these two ways should give us the same volume under the surface. So let's calculate this way first. Okay, so we have v equals integral from 1 to 2, integral from 1 to 7 minus 3y. We're integrating x times y with respect to x first, and then with respect to y. All right, so integrating x times y with respect to x first. We have a half x squared times y. And then that's with respect to x. So I like to point out that it's x equals 1 and x equals 7 minus 3y. These are our bounds. It's in terms of x. So I'm replacing the x when I do that. Okay, so we've got integral from 1 to 2, and then here we're subbing in x equals 7 minus 3y, so 1/2 7 minus 3y squared times y, and then subtracting, subbing in x equals 1, so 1/2 1 squared times y. Okay, so now we want to expand and simplify this. So there's a 1/2 in both, so let's pull that 1/2 out. And so 7 squared is 49. But then we multiply it by y. Okay, 7 times 3 is 21, but doubling that because it's getting squared. So minus 42 y, but then it gets multiplied by y, so we have a y squared. Okay, then minus 3 squared is 9, so this is plus 9 y squared times another y is y cubed. And then we, having factored that 1/2 out, we have minus y. Okay, so we can do a little bit more simplifying before we integrate. So 49 minus 1 is 48. If we divide that by 2, taking that half back in, then we have half 48 is 24. Okay, half of 42 is 21. And then half of 9 is 9/2. All right, so we now have a fairly simple integral to calculate. So adding 1 to the exponent and dividing by the new exponent here, y squared 24/2, that's 12 y squared. Okay. Adding 1 to 2 gives 3, dividing by the 3, so we've got minus 7 y cubed. 3 plus 1 is 4. 2 times 4 is 8, so plus 9/8 y to the power of 4. So this is 1 to 2. Okay, good. So we've got to sub in 2, sub in 1, and take a difference. So 2 squared is 4. 4 times 12 is 48. Okay, 2 cubed is 8, so that's minus 7 times 8 is 56. 2 to the power of 4 is 4 squared is 16. 16/8 is 2. So 9 times 2 is 18. Okay, now we subtract 12 minus 7 plus 9/8. All right, so now 48 and 18 gives 66. 66 minus 56 is 10. Now 12 minus 7 is 5. So 10 minus 5 is 5. And then bringing that minus over. So 5 minus 9/8. So we can write this as 5 times 8 is 40. So 40 minus 9/8. 40 minus 9 is 31. So we get 31/8 as our volume. And you can give an approximation for that. All right, now let's calculate this the other way. So in the other way, we want to perform this. Hang on, I'll bring it down. In the other way, we want to perform this calculation. And we hope to get 31/8. Okay, so the volume the other way is the integral 1 to 4. And then on the inside, we have 1 to 7 minus x over 3. Integral of x times y, doing with respect to y first, and then with respect to x. Okay, so integrating xy with respect to y. we have a half xy squared from y equals 1 to y equals 7 minus x over 3. Okay, so we've got to sub these two values in for y and take a difference. So 1/2 x times 7 minus x over 3 all squared. And then we're subtracting 1/2 x times 1 squared. Is that right? Yeah, so now at this point I've subbed it in, so I really want round brackets here. Okay, there's a common 1/2. I can bring that factorizing it out the front, which would make the calculation look a little bit easier. Okay, so let's do that. Bring the half out the front. So squaring 7 minus x, and then it's all over 9 because 3 squared is 9. So we have 1/9. 7 squared is 49. Then it gets multiplied by x. And then, having factored out the half, we subtract 1, so we get 48x. Okay, now 7 times 2 is 14. So minus 14x, but then we multiply by another x, so we've got x squared. Okay, x minus x all squared is x squared. Again, that's over 9 because we've got a 3 squared there. Multiply by another x, and so we have plus x cubed. All right, so we have this. Is that right? Hang on. No, not quite. I've done a little bit too much in my head and got something wrong. So, because this is over 9, right, when we square that, but then what we subtract away is a whole 9. So this should be 40, not 48. Okay, good. So now, to complete this, we can pull that 1/9 out. Call this 1 over 18 out here. And now let's integrate this. So the integral of x is x squared over 2. So we have 20x squared for this piece. Integral of x squared is x cubed over 3, so we have minus 14 over 3x cubed. The integral of x to the 3 is x to the 4 over 4. Okay, subbing the numbers in, so 4 squared is 16. 16 times 20 is 320. Now 4 cubed is 64. So I'm going to write minus 14 over 3 by 64. And then 4 to the power of 4 is 16 squared is 256, but then we divide that by 4, so this is really 4 cubed. Now 4 cubed is 16 times 4 is 64. Okay, and then we are subtracting 20 minus 14 over 3 plus 1/4. All right, so let's simplify this. Let's look at the integers first. So that's 384 minus 20 gives 364. Okay, now this little piece, that's a plus 14 over 3. So I can write this minus 14 over 3, 64 subtract 1. When you multiply that minus back in, you get a plus 14 over 3. Okay, and then there's a lonely minus a quarter. So I did this because 63 is divisible by 3. So we've got 21 times 14. Okay, so now I'm going to get Mathematica to do a little bit of helping. Just put this in here. So we have 364 minus 14 times 21, and then minus 1 over 4. Okay, that gives us, and it's under my head, so I'll scroll up, that gives us 31 over 8. That's what we got earlier, which is fantastic. So we did a really hard integral, calculated in 2 ways, and we got the same answer. All right, so now we're going to look at the integral on the right-hand side of figure 30, which is this really, taken in another way. So in the first way, it's easy. In the second way, it's a real pain. But we're going to do that in both ways. All right, so here's our region. It looks like this. So x goes from 0 to 2, and y goes from minus x to x squared. The surface is x squared plus y squared, so we have the volume equal to the integral minus x to x squared, integrating x squared plus y squared. Now that's with respect to y first, and then with respect to x. All right, so I'm going to put this over here now. So integrating this with respect to y, we have x squared y, and then plus 1/3 y cubed, from y equals minus x to y equals x squared, and then we've got to integrate that with respect to x. Okay, so subbing in y equals x squared, we've got x to the power of 4. And then doing the same thing here, we've got 1/3 x to the power of 3 times 2 is 6. Now, subbing in x, or subbing in y equals minus x, so we subtract, that's minus x cubed. And then again, replacing minus x in there, minus x cubed is minus x to the power of 3. All right, so if we add these two, that's minus 4/3 x cubed. Minus 4/3 x cubed is plus 4/3 x cubed. Okay, so now it's just a polynomial to integrate. So we have 1/5 x to the 5th. We have 1 over 3 times 7 is 21. X to the 7th. 3 plus 1 is 4, so we're dividing by 4. That gives us 1/3 x to the power of 4. We have bounds 0 and 2. Okay, now if we sub in 0 into each of these, we get 0, so we're going to subtract 0. So we've got 2 to the power of 5 is 32. 2 to the power of 7 is 32 times 4. And then 2 to the power of 4 is 16. All right, so if you do the sums, you'll get 624 over 35 for this. Okay, now to swap the order of integration, well, this is quite tricky now because you've got to view this region as a disjoint union of two regions. So the first one, so from y goes from 0 to 4, this would be this region, and so let's call this R1 union R2. So here's our dashed line. So if I call this one R1, then y is going from 0 to 4. And then in the second little piece underneath that, R1, we have y going from -2 up to 0. Okay, so I've got to break it up here if I insist on swapping this around. And so sometimes you want to do that because the integral itself would be easier one way rather than the other way. All right, and so here the x value in this changing of order, so the top of that is 2. So x equals 2. The bottom of that is x equals 0. X is above the square root of y. So this here would be the curve, x equals square root of y, or y equals x squared. So x is to the right of that, so x is above square root of y, or equal to it, and less than or equal to 2. Now here, this line is the line x equals minus y, or y equals minus x. So let's put x equals minus y, and so x is to the right of minus y in this region down here. Y is still between -2 and 0 in this region. I should call that R2, right, rather than R1. Okay, so here is R2, this is R1. And so writing this the other way, well, what we're doing is we're calculating this volume, and adding those together. All right, so doing this is what it looks like, and then plus this. Okay, so let's do some of this at least. And since it's probably going to take up more page, well, you can write small, but I'll probably end up doing the rest of the calculation here in Mathematica because it's just virtually impossible to get wrong. Okay, so integral from 0 to 4. Now integrating this little piece with respect to x gives us 1/3 x cubed plus x y squared, and we are subbing in x equals root y and x equals 2. And then we've got to integrate the result with respect to y. So that's just that little piece, right? Okay, now for this one, same integral with respect to x. So 1/3 x cubed plus xy squared as x goes from minus y up to 2, and then we integrate the result with respect to y. Okay, so now we're making the replacements. We still have the integral from 0 to 4, but this little piece is going to be a little bit large. So 2 cubed is 8, so 8 over 3. 2 squared is 4, so plus and plus 4. No. Okay, what am I replacing? I'm replacing x with 2. So 2y squared. Yes. And then we subtract what happens when we replace x with root y. So that would be 1/3 y root y, or y to the power of 3 over 2, and then plus y squared root y. And so all of this gets integrated with respect to y. Okay, so this little bit is just what we have here on the left. Now let's have a look at this. So you can see it's probably a bit more of a pain to do it this way than it was to do this, because this was fairly simple. Okay, so 2 cubed is 8. 8 over 3 plus 2y squared so minus, now we're replacing x with minus y, so that's minus y cubed over 3, and then minus y cubed. Okay, and so simplify this, you're going to get 624 over 35 again. Should we just double check? Let's get the machine to double check. So just so you see I'm not cheating, 1 plus 1 is 2. All right, integrate. Now it's with respect to y, as y goes from 0 to 4. Okay, so what we are putting in there, I'm just going to copy this. So 8 over 3, then we have plus 2y squared. I'm subtracting 1/3 y root y. So there. Okay, then I have plus y squared root y. Okay, so that's that piece. Let's integrate that numerically. So the first piece, we're going to get 1312 over 105. Okay, so that is, that's this little segment, the volume over R1. Okay, and then we add to that the other piece. And that other piece was 8 over 3 plus 2y squared minus 1/3 y cubed, but it was minus inside there. And then minus y cubed. Okay, so I see the issue here. I've got to integrate from minus 2 to 0 in the second piece, so that's should be minus 2 to 0 here. And so this gives us 16 over 3 when we do this little calculation. So 16 over 3. Now the sum of these two things (624 over 35).